Hey everyone, welcome back to the deep dive. You know the drill, right? We take something complex, something you want to understand better, and we break it down together.
Today, we're tackling the world of real numbers.
And more specifically, two pretty fundamental ideas from number theory, the fundamental theorem of arithmetic.
And how it connects to something you might not expect, irrational numbers.
Yeah, we'll be using this document called gem101.pdf as our roadmap. Think of it as a deep dive inside a deep dive.
We'll be pulling out the key concepts, the surprising connections.
You're really trying to unpack why these ideas matter, why they're more than just abstract math.
Right, so there are two main areas we'll be exploring. First up is the fundamental theorem of arithmetic itself. We'll look at what it says, why it's so important,
And how it's connected to concepts you might remember from school, like prime factorization, HCF, and LCM.
and then we'll shift gears to irrational numbers, those numbers that can't be written as simple fractions.
We'll revisit what they are.
And then here's the really interesting part.
We'll see how the fundamental theorem of arithmetic actually gives us a way to prove that numbers like the square root of 2 or the square root of 3.
Are irrational.
So, are you ready to dive in?
Let's do it.
Okay, so let's start with the fundamental theorem of arithmetic. Basically, it says that any composite number, and remember, a composite number is any whole number greater than one that isn't prime, can be expressed or written.
As a product of prime numbers.
Yeah, and the important thing here is that it's not just a way to write them as a product of primes. It's the only way.
That's right. It's unique. Apart from the order you write those primes, there's only one prime factorization for each composite number.
Right, so like 2 times 3 is the same, essentially, as 3 times 2.
Mm-hmm.
Same prime factors, just in a different order.
Exactly. It's like every composite number has its own unique prime fingerprint.
Love that, a prime fingerprint. So the document mentions that while this idea has been around for a while, even back to Euclid,
It was Carl Friedrich Gauss who really formalized it, gave it a rigorous proof.
and that's why it's considered so fundamental to number theory. It's like a cornerstone.
Yeah,
But okay, let's get practical here.
sure.
How does this theorem actually help us do anything?
Well, the document gives a few really good examples. Like example 1 asks whether a number like 4 to the power of n, where n can be any whole number.
Can ever end in the digit 0?
And the fundamental theorem gives us a really straightforward answer. If a number ends in 0, it has to be divisible by 10.
Which means it has to have both 2 and 5 in its prime factorization.
Right. Now think about 4 to the power of n. That's the same as 2 squared, all to the power of n.
Which simplifies to 2 to the power of 2nn.
And because of that unique prime factorization we talked about, the only prime factor 4 to the power of n will ever have is 2.
No 5 anywhere.
Exactly. So it can never, ever end in a 0.
So cool, right? Just by understanding the prime building blocks of a number, we can figure out some pretty interesting things about it.
Well, it's powerful stuff.
Yeah.
And the document also reminds us how this theorem is at work when we find the highest common factor, or HCF.
And the least common multiple, or LCM, of numbers. Remember those?
Oh, yeah. We use prime factorization for that. You find all the prime factors the numbers share, and then for the HCF, you multiply them together.
Using the smallest power of each prime that shows up in both numbers.
And for the LCM, you take all the primes in either number and multiply them, but this time you use the highest power of each prime.
Right. So, for example, if you have 6 and 20,
6 breaks down into 2 times 3.
and 20 is 2 squared times 5. So the HCF is just 2.
Because that's the only common prime factor, and the lowest power it appears in is 2 to the power of 1.
For the LCM, we need all the primes, so 2, 3, and 5, and we use the highest power of each.
So 2 squared from the 20.
3 to the power of 1 from the 6, and 5 to the power of 1 from the 20. Multiply those all together, and you get...
260.
Now, here's something interesting the document points out. If you take the HCF of two numbers and multiply it by the LCM of those same two numbers,
You always get the same answer as if you just multiply the original two numbers together. Like with 6 and 20, the HCF was 2, the LCM was 60.
2 times 60 is 120, which is the same as 6 times 20. Pretty neat, huh?
Yeah, it is. The document also goes through examples of finding the HCF and LCM for larger numbers.
Like 96 and 404.
And even 3 numbers. 6, 72, and 120.
But there's a catch when you're working with more than two numbers.
Right. There's a little remark in the document that's really important. That nice relationship between the HCF, LCM, and the product, it only works for 2 numbers.
If you have 3 or more numbers, it gets a bit more complicated.
Actually, at the very end, in a note to the reader, they give the correct formulas for 3 numbers, and they involve calculating pairwise HCFs and LCMs. It's not as straightforward.
Okay, good to know. So the document then moves on to some exercises, exercise 1.1.
A lot of them are about using the fundamental theorem directly, like expressing numbers as products of their prime factors,
And there are questions about finding the HCF and LCM too.
which really helps solidify those concepts.
Question 5 is kind of interesting. It asks if 6 to the power of n can ever end in the digit 0.
Ah, similar to the 4 to the power of n problem.
Exactly, and we can use the same logic, right?
Yep. 6 only has the prime factors 2 and 3. So 6 to the power of n, no matter what n is, will only ever have 2 and 3 as its prime factors.
No 5.
So it can never end in 0.
Question 6 is a good one too. Gives you these expressions like 7 times 11 times 13 plus 13.
And 7 times 6 times 5 times 4 times 3 times 2 times 1 plus 5.
And it asks you to explain why they're composite numbers.
Well, the fundamental theorem helps us see that these numbers must have factors other than 1 in themselves.
Right. In that first one, you can factor out a 13, and in the second one, you can factor out a 5.
So they're not prime.
And then question 7 is that classic problem where you have two people running around a track.
Rania and Ravi.
Sonia takes 18 minutes to complete a lap, and Ravi takes 12 minutes. And the question is, when will they both be back at the starting point at the same time?
Sounds like a job for the LCM.
Exactly. You just find the LCM of 18 and 12, and that tells you how many minutes it will take. And to find the LCM,
You can use prime factorization just like we've been talking about.
so the fundamental theorem of arithmetic isn't just some theoretical thing. It's a really practical tool for understanding and working with whole numbers.
It really is.
Okay, so we've seen how powerful this theorem is when it comes to composite numbers. But, as I mentioned earlier, its influence reaches even further.
Into the realm of irrational numbers.
Exactly. It's kind of mind-blowing that this idea about prime factorization can help us understand numbers that can't even be expressed as fractions.
So just to remind everyone, irrational numbers are numbers that can't be written in the form p over q, where p and q are integers and q isn't 0.
Right, like the square root of 2, the square root of 3, pi.
Those are the classics. And to prove that a number is irrational, there's this really useful stepping stone, which is theorem 1.2 in the document.
What does that one say?
It says that if you have a prime number, an EP, and it divides a squared where a is a positive integer.
Then p must also divide a itself.
Okay, that makes sense, but how do we know that's true? It all goes back to that unique prime factorization we were talking about. When you square a number, you're essentially squaring all of its prime factors.
Right.
So if a prime number p is a factor of a squared, it means it had to be a factor of the original number a as well.
Because otherwise, where would that p have come from in the prime factorization of a squared?
Exactly. So that theorem, theorem 1.2, it's a really important consequence of the fundamental theorem of arithmetic.
And it's key for proving irrationality. Like, the classic example is proving that the square root of 2 is irrational.
Right. And the way we do that is using a proof by contradiction.
Which sounds fancy.
It's actually a pretty clever strategy. You start by assuming the opposite of what you want to prove. So in this case,
We assume that the square root of 2 is rational.
right. And if it's rational, it means we can write it as a fraction, a over b, where a and b are integers and b isn't 0.
And we can always simplify that fraction so that a and b don't have any common factors other than 1. They're what we call coprime.
Right, coprime. So we start with that assumption. The square root of 2 equals a over b, where a and b are coprime.
Okay, what's next?
Well, now we square both sides of that equation. So we get 2 equals a squared over b squared.
And if we rearrange that a bit,
We get 2 times b squared equals a squared.
which means that a squared is a multiple of 2.
Right. And this is where theorem 1.2 comes in. If 2 divides a squared, then it must also divide a.
Meaning a has to be an even number.
Exactly. So we can write a as 2 times c, where c is some other integer,
Okay, so let's substitute that back into our equation. 2b squared equals 2c, all squared.
which simplifies to 2 times b squared equals 4 times c squared.
And if we divide both sides by 2,
We get b squared equals 2 times c squared.
and look at that. Now we see that b squared equals 2 times c squared,
And look at that. Now we see that b squared is also a multiple of 2.
which, using theorem 1.2 again, means that b must also be divisible by 2.
And here's the problem. We started by assuming that a and b were coprime, that they had no common factors other than 1.
But now we've shown that they're both divisible by 2.
That's a contradiction.
Right. Our initial assumption that the square root of 2 is rational led us to something impossible.
Which means our initial assumption must be wrong.
So, the square root of 2 must be irrational. Boom.
It's a really elegant proof.
Yeah, it's amazing how this seemingly simple idea about prime factorization can lead to such a powerful conclusion.
The document also walks through a similar proof for the square root of 3 in example 5.
Oh, right. I remember seeing that. It uses the same kind of logic, just with a prime number 3 instead of 2.
Exactly. So the fundamental theorem of arithmetic, it's not just about composite numbers.
It's a key to understanding irrational numbers as well.
It is. The document also mentions some important properties of rational and irrational numbers, like
If you add or subtract a rational number and an irrational number,
the result is always irrational.
and the same goes for multiplying or dividing a non-zero rational number by an irrational number.
The result will always be irrational.
And they give some examples of how to prove those properties
Hmm.
in examples 6 and 7.
Right. They show that 5 minus the square root of 3 is irrational.
And that 3 times the square root of 2 is also irrational.
And then there's exercise 1.2, which has a bunch of problems where you can practice proving the irrationality of different numbers.
Like the square root of 5, or 3 plus 2 times the square root of 5.
And even some expressions like 1 over the square root of 2, 7 times the square root of 5, and 6 plus the square root of 2.
All good practice.
The document wraps up with a nice summary of the key points about the fundamental theorem of arithmetic and how it's used to prove irrationality.
And let's not forget that a note to the reader at the very end.
Right, about the HCF and LCM for 3 numbers.
Yeah, it's a good reminder that while the HCF times the LCM equals the product of 2 numbers, it doesn't work quite the same way for 3.
They give the correct formulas in that note.
So there you have it. We've gone deep into the fundamental theorem of arithmetic and its connection to irrational numbers. It's amazing how such a simple-sounding idea has such far-reaching implications.
What's really cool is that this understanding of prime numbers and how they build up other numbers, it's like the foundation for so much more in math. Like even the way we write decimals, it all comes back to prime factorization.
Wow, I never thought of it that way. So as you go about your day, think about this idea of unique building blocks. We saw it with prime numbers for integers, but it pops up in so many other places too. How does that idea of unique components shape how we understand the world around us, not just in math, but in everything? It's something to ponder, for sure. Anyway, that's it for this deep dive. Thanks for listening.
Thanks for joining us.